So, the sun does not produce energy by just, oh, here are four hydrogen atoms and oop, they hit each other and now we have a helium. It's not that simple. There's kind of a few steps that it has to go through to build up to getting to that final step of making a helium atom. And those series of steps are called the proton chain. So, I'm basically just going to kind of draw out a diagram of the proton-proton chain so y'all can see how it works. You start off with four hydrogen atoms, four protons, and they are in the extreme heat and pressure of the sun's core. So what's going to happen? So under this extreme heat and pressure, these two hit each other, and these two also hit each other separately. And what's produced here is not a helium atom, but a hydrogen atom with a neutron. I'm drawing the neutron in black to indicate that it is neutral. It doesn't have an electric charge, as opposed to the protons, which are positively charged, so I've drawn them as red. Now this is unusual. Usually hydrogen is just a proton with an electron around it. Usually hydrogen does not have a neutron. So this is like a special hydrogen that does have a neutron. But this isn't all that happens. See, effectively here what's happened is that one of these protons turned into a neutron as part of the process that happened here in this collision. But you might be wondering, where did its positive charge go? Did it just disappear? Well, no. Because in addition to this stage of the process also produces one positron. A positron is like an electron, except positively charged instead of negatively charged. So this positron effectively takes the positive charge of the proton that turned into a neutron. This stage of the process also releases one neutrino. Neutrinos are very, very small particles, much less massive even than like an electron. And neutrinos, as I've indicated by drawing them in black, do not have an electric charge. They're neutral. And so this means that they interact with almost nothing, right? Like, the reason that solid objects can't pass through each other is that their electrons, which are all negatively charged, push against the other electrons, which are also negatively charged, and they repel each other. But since neutrinos don't have a charge, electrons don't bother neutrinos. They don't push on them. So neutrinos can just go through atoms. The only time a neutrino really interacts with an atom is if it hits the atom's nucleus directly. And this is very rare because atoms are mostly empty space. Relative to the total size of the atom, the nucleus is very small. So yeah, neutrinos barely interact with anything, and one gets created at this stage in the process. Meanwhile, over here, the exact same thing happens. You have your proton, you have your hydrogen with a neutron in it. You have your positron, and you have your neutrino. the next step. In comes two more protons. They were around in the same environment, but not involved in the process that these ones were going through until now. Now they're entering into the situation. And they each collide with the hydrogen with a neutron. And as a result of this collision, what we get is a helium with one neutron. This is also unusual. Normally, heliums have two neutrons, but here we have two heliums that each only have one neutron. And additionally, as part of this reaction, they both emit one photon of gamma radiation. One gamma photon is also emitted as part of this step. Finally, these two heliums with one neutron collide with each other, forming a normal helium, a helium with two neutrons, and two free hydrogen atoms, two protons, right? You have three here, that's a total of 6. So then you've got these 4 and 2 left over. And they just become free protons, kind of in the same situation they were at in the beginning. Maybe they can now go on to participate in another proton-proton chain. So yeah, that's how the process works. Now it is actually a little more complicated than this. See, at this point, where you've got the two heliums with one neutron, there are actually a few different things that they can end up doing at that point, other than what I've drawn here. And those are all variants of the proton-proton chain. What I've drawn here is called variant 1, or PP1. But there's also a PP2, a PP3, and a PP4. Now PP1, we think, accounts for about 83% of the energy that the sun produces. And so PP2, PP3, and PP4 together make up about 17%. So they're definitely significant, right? That 17% of the sun's energy is definitely a significant amount, but they're also a lot more complicated, they're harder to remember, and, you know, when PP1 is just this dominant, then, yeah, basically you only need to remember PP1. It's nice to know that PP2, 3, and 4 exist, but you don't actually need to learn what they are. Just PP1. So with that, I think that about covers this video. In the next video, I'll be talking about basically why is the sun the size that it is instead of a different size.